Consciousness, the experience of being aware, remains one of the greatest mysteries in science. How does the brain create the rich, unified experience of sight, sound, thought, and feeling? Classical neuroscience explains much about how neurons fire and networks communicate, but many questions remain. How do billions of neurons produce one seamless conscious experience? How does the brain bind sensory information, or create the sense of time passing? One bold idea proposes that consciousness may arise not only from neurons, but from quantum processes inside them. This is the Quantum-Orchestrated Consciousness theory, or QOC, a modern evolution of the Penrose, Hameroff, Orch-OR model, updated with the latest scientific understanding. Inside every neuron are tiny cylindrical structures called microtubules. These structures act like scaffolding, giving the neuron shape and transporting molecules. But QOC proposes they do something extraordinary. Microtubules may support quantum states, tiny delicate arrangements of particles that can exist in multiple possibilities at once. In QOC, microtubules are modeled as resonant cavities where tubulin proteins interact with structured water molecules and electromagnetic fields. These interactions create entangled quantum states, potentially lasting microseconds to milliseconds, long enough to influence the neuron's activity. Quantum states in microtubules are tiny, but QOC explains how they influence the whole brain. These microstates can subtly affect voltage-gated ion channels and the axon initial segment, where neurons decide whether to fire. QOC retains the idea of objective reduction, first suggested by Roger Penrose. In this model, when a quantum state reaches a certain energy threshold, it collapses into a single outcome. But QOC adds a modern twist. This collapse is orchestrated. The neuron and its network help determine which quantum states collapse, creating meaningful events in consciousness rather than random noise. This forms a feedback loop. Quantum states influence neurons, which influence networks, which in turn guide future quantum events. One of the most puzzling aspects of consciousness is the binding problem. How the brain combines sights, sounds, and thoughts into one unified experience. QOC proposes that entangled microtubules across neurons synchronize, aided by brain oscillations like gamma waves. This quantum synchronization helps bind sensory information together, creating a seamless conscious experience. Anesthetics provide a unique test of the theory. QOC suggests that anesthetics work by disrupting microtubule quantum coherence, temporarily blocking consciousness. This idea actually aligns with experiments showing anesthetics interact with tubulin. Unlike classical models, QOC explains why we lose awareness without immediately stopping neuron firing. Consciousness depends on orchestrated quantum events, not just action potentials. QOC doesn't reject classical neuroscience. Instead, it complements it. For example, with integrated information theory, quantum coherence enhances the amount of information integrated across neurons. And then with global workspace theory, quantum events improve the precision and timing of information broadcasting. Finally, when it comes to predictive processing, quantum states may fine-tune how the brain predicts and interprets sensory input. Critics of quantum consciousness models have raised three main concerns. First, decoherence. Quantum states are fragile and may collapse instantly. QOC addresses this by showing how metabolic energy and microtubule structure can actually sustain coherence longer. Second, the causal link. Evidence connecting quantum microstates to conscious experience is, well, still indirect. QOC provides a mechanistic bridge through ion channel modulation and network amplification. And third, testability. Critics argue the theory is hard to test. QOC makes clear predictions. Microtubule coherence can be measured in neurons, quantum collapse events should correlate with EEG patterns, and anesthetic effects can be studied in controlled experiments. QOC is scientifically ambitious but testable. For example, researchers can detect microtubule quantum coherence using spectroscopy or spin resonance techniques. They can observe correlations between quantum collapse events and EEG gamma oscillations. It's also possible to study how anesthetics selectively disrupt coherence while leaving classical firing intact, and computational models can be used to simulate how quantum states influence neural network behavior and perception. In the quantum-orchestrated consciousness theory, awareness emerges from a delicate orchestration of quantum events, neuronal firing, and network synchronization. It's really a hybrid system. Quantum precision amplifies classical computation, explaining the unity, timing, and richness of conscious experience. While still a bold hypothesis, QOC integrates modern physics, neuroscience, and biophysics into a coherent framework, offering a scientifically plausible explanation for consciousness that can be tested, refined, and explored in future research. If you're fascinated by the mysteries of consciousness, subscribe for more videos exploring the brain, quantum science, and the nature of mind.